If you hold a statically charged pipe next to a falling stream of top water, the water physically reaches for it. But if you try the exact same experiment with a stream of cooking oil, the liquid falls straight down. It ignores the electrical charge entirely. Water is a neutral liquid. It has no metallic properties, so a basic electrical field shouldn't exert this kind of physical pull on it. To understand why oil acts dead to the charge while water reacts to it, we have to zoom past the liquid state and look at the physical shape of the molecules themselves. Every chemical bond is a continuous tug-of-war. The atoms inside a molecule are constantly trying to pull negatively charged electrons toward their own centers. Look at this 3D model of carbon dioxide. It has a perfectly straight, linear geometry. Two vector arrows represent forces pulling in exact opposite directions. Because these opposing forces are perfectly symmetrical, they crash into each other in the center and cancel out completely. Chemists refer to this balanced state as having a net dipole of 0. That perfect architectural symmetry leaves the molecule chemically inert, rendering it completely blind to outside magnetic or electric forces. Now compare that to this water molecule. Notice the geometry. It's bent. The two hydrogen atoms sit at an angle. Because the atoms are angled, your pulling forces no longer cancel each other out. Instead, they fuse together into a single massive upward force. That combined master arrow is called the dipole moment. It leaves one end of the water molecule permanently positive and the opposite end permanently negative. That slight structural asymmetry means every single molecule of water acts like a tiny permanent magnet. This animation shows thousands of individual water molecules in their natural state. They vibrate and spin chaotically, with their internal magnets pointing in random directions. But watch how they react if we introduce a strong external electric field with a positive and negative plate. The chaotic molecules violently snap into perfect military alignment. They all point their dipole moments in the exact same direction. This is polarization. This microscopic alignment is the exact mechanical phenomenon that powers one of the most common appliances in human history. Those causative and negative plates we just observed act exactly like the inner walls of a microwave oven. By figuring out how to manipulate that tiny dipole moment, engineers developed a way to generate extreme heat without a flame. This diagram shows the core mechanism: a microwave blast radiation at 2.4 gigahertz, an electric wave that rapidly alternates between positive and negative. The water molecules violently flip 180 degrees back and forth to stay aligned with the shifting wave. Forcing billions of polar molecules to flip back and forth billions of times a second generates massive physical friction. The heat that cooks your food is entirely self-generated. It comes from the violent friction of water molecules fighting to keep their dipole moments aligned. Which brings us back to the falling streams of liquid. The water bends toward the charged rod because it is packed with massive dipole moments. It is a polar liquid. The oil ignores the charge because its molecules are perfectly symmetrical and neutral. It is nonpolar. The microscopic geometry of a molecule acts as an invisible ruler. It dictates exactly how every single liquid behaves, sorting the entire physical world into strictly polar or nonpolar.